The oldest photograph of our universe hides a secret code. This image is the cosmic microwave background, the faint afterglow of the Big Bang. But scientists have found it is not a simple picture. It contains 48 hidden patterns, cosmic anomalies that defy every explanation our current physics can offer. By the end of this journey, you will understand how these flaws in the cosmic blueprint could rewrite the story of everything. Why does the universe have a preferred axis, a so-called axis of evil? What created a mysterious cold spot so vast it should not be there? These are not minor details. They are cracks in the foundation of modern cosmology. What does it mean when the universe itself seems broken? That faint glow is the universe's baby picture, taken before the first star ever ignited. To read the secrets hidden within it, we need to understand exactly what we are looking at. The cosmic microwave background is the oldest light in existence, a fossilized echo of the Big Bang's explosive birth. It was created when the cosmos was just 380,000 years old. Before that moment, the universe was a searing, opaque fog, a thick soup of particles and energy where light was constantly trapped, bouncing from one particle to another. Then, in an event cosmologists call recombination, the expanding universe cooled just enough for atoms to form. Suddenly, the fog cleared. The light that had been imprisoned within that plasma was set free, streaming across space for the very first time. That first flash of liberation is what we detect today as the CMB. After traveling for over 13 billion years, the energy of that light has been stretched and diluted by the expansion of the universe, cooling it down to a mere 2.7 degrees above absolute zero. It is a cold, uniform bath of radiation that permeates everything, but its near-perfect uniformity is the first clue that something deeper is at play. When scientists created a detailed map of its temperature, they found it was not perfectly smooth. The map is speckled like an old television screen tuned to static. These tiny variations, minuscule differences in temperature of just 1 part in 100,000, are the most important features in the cosmos. They are the imprint of the earliest quantum ripples, the gravitational seeds from which every galaxy, every star, and every planet would eventually grow. Our entire cosmic neighborhood, everything we see, was born from these infinitesimal wrinkles in space-time. So when astronomers discover patterns within these wrinkles that should not exist, they are not just finding curiosities. They are finding flaws in the very blueprint of reality, and the first flaw is perhaps the most unsettling of all. This alignment is so profound it earned a dramatic name, the axis of evil. Imagine spinning a globe and finding that every single continent, every mountain range, is subtly tilted to point toward the North Pole. That is the level of strange order scientists found in the universe's chaotic infancy. The largest warm and cold spots in the cosmic microwave background are not scattered randomly. Instead, they appear to align along a specific corridor of space, a preferred direction that should not exist. The fundamental assumption of modern cosmology is that the universe is isotropic. This is a fancy way of saying the cosmos has no center and no edge, and it should look essentially the same from any vantage point. There should be no up or down, no left or right on a cosmic scale. The axis of evil is a direct challenge to that idea. It hints that the universe might have an architecture, a large-scale structure that privileges one direction over all others. Is this axis a ghostly imprint from a time before the Big Bang, a scar from a collision with another universe, or could it be something far more local, a distortion caused by our own solar system's journey through space? Even after accounting for our motion, the anomaly stubbornly remains. This leaves us with a haunting possibility. What if the universe is not the same in every direction? What if we are living in a cosmos with a built-in preference, a fundamental skew that we are only just beginning to perceive? The mystery does not end with a single axis. Yet the axis of evil is not the only ghost in the machine. Far from the strange alignment in the southern galactic hemisphere, the cosmic microwave background holds a different kind of flaw. A vast frigid patch known simply as the cold spot. This region is not just a little cooler than its surroundings. It is a profound and unexpected chill, an area so large and so cold that it stands out like a frozen continent on the map of the infant universe. Its very existence pushes against the boundaries of our most trusted cosmic models. According to the standard story of cosmic inflation, the early universe should be a tapestry of random quantum fluctuations. The temperature variations we see should be like the texture of an orange peel, with a certain predictable range of sizes and depths. The cold spot, however, is more like a massive, smooth crater. Its scale and its sharp temperature drop are statistical outliers. It is a feature that, by all rights, should not be there. The most straightforward explanation scientists proposed was a cosmic emptiness. If a gigantic supervoid, a region of space with a startlingly low density of galaxies and matter, lay between us and the cold spot, it could theoretically create the illusion. As light from the cosmic microwave background passes through such a void, it would lose a tiny amount of energy climbing out of the void's weakened gravitational field, a process called the integrated Sachs-Wolfe effect. This energy loss would make the light appear colder. It is a plausible, physics-based answer, but when astronomers pointed their telescopes toward the cold spot, they found nothing. Or rather, they did not find nearly enough nothing. The supervoids they discovered were far too small and too shallow to account for the dramatic coldness observed. The evidence needed to support the theory simply was not there. With conventional explanations failing, more speculative ideas emerge. Could the cold spot be a cosmic bruise, the imprint of a collision with another universe? In the multiverse scenario, our universe is one bubble among countless others in a frothing sea of eternal inflation. If our bubble had gently bumped into a neighboring one in the distant past, the energy of that collision could have left a scar on our sky, a permanent cold spot on the cosmic background. It is a breathtaking possibility, suggesting that the cold spot is not a flaw in the universe, but a window to what lies beyond it. Whether it is a failed supervoid or a sign of a multiverse, the cold spot remains a persistent enigma. It is a localized mystery that challenges the global picture, forcing us to ask if our universe is truly as random as we believe. But the anomalies do not stop with single, dramatic features. The plot thickens when we look at the patterns that emerge across the entire sky. But the strangest patterns are not found in dramatic spots or mysterious axes. They are found in the quiet statistics, in what the universe's blueprint fails to show. When cosmologists analyze the map of the cosmic microwave background, they expect to see a certain amount of connection, a subtle conversation between different parts of the sky. On the largest scales, however, that conversation falls silent. Regions of the universe separated by more than 60 degrees appear to have nothing to say to each other. They are cosmic strangers, islands too far apart to have ever exchanged a signal, and according to our most fundamental laws of physics, that is exactly how it should be. The problem is that these distant regions look far too similar. They share a common temperature, a common texture, as if they were once in perfect sync. But how could that be possible? In the early universe, light had only a finite amount of time to travel. 2 points on opposite sides of the sky were simply too far apart for any information. any influence to have traveled between them by the time the cosmic microwave background was created. They were beyond each other's cosmic horizon, forever out of touch. This is the horizon problem, and it was one of the great puzzles that led to the theory of cosmic inflation. The idea is as radical as it is elegant. Perhaps in the first fleeting fraction of a second, the universe underwent a period of unimaginably rapid expansion, ballooning from a subatomic speck to something much larger in an instant. This inflationary burst would have stretched a tiny, interconnected patch of space into our entire observable universe. Those distant regions that seem like strangers were actually next-door neighbors in that primordial moment, able to synchronize before inflation flung them apart. It is a brilliant solution that explains the large-scale smoothness. Yet, like so much in cosmology, the story is not so simple. While inflation explains why the universe is correlated, the precise data from the cosmic microwave background reveals a new twist. The universe is not just smooth, it is too smooth. The expected correlations on the very largest scales are even weaker than the simplest models of inflation predict. It is as if the universe's volume was turned down on the grandest symphony of all. This puzzling lack of correlation is a subtle but profound statistical ghost. It suggests that our inflationary models, for all their power, might still be missing a crucial piece of the puzzle. Perhaps inflation happened differently than we think, or maybe something else entirely suppressed the universe's largest structures. This quiet anomaly connects to a deeper question about the very shape of reality. Is the geometry of our universe not what it seems? Even the statistical quiet of the largest scales is not the final word on these cosmic irregularities. Deeper within the mathematical heart of the cosmic microwave background lies a clue so specific it feels almost personal. Scientists break down the map of the ancient sky into what they call multipole moments. These are not physical objects but mathematical descriptions, each one capturing a different rhythm or pattern of hot and cold spots across the cosmos. The dipole moment describes the overall temperature difference caused by our motion through space. The quadrupole, the next moment, captures a more complex, four-lobed pattern of warmth and chill. The octupole is even more intricate, an eight-lobed arrangement. In a universe that is supposed to be random and isotropic, these different patterns should be oriented independently, pointing in random, unrelated directions. They should be cosmic strangers to one another, but they are not. The quadrupole and the octupole, two of the most fundamental patterns in the universe's infancy, are aligned. Their axes point in the same general direction. This alone is a strange statistical fluke. The mystery deepens exponentially when you discover what else they are aligned with. The plane of this curious cosmic alignment is not arbitrary. It coincides eerily with the ecliptic plane of our own solar system, the flat disk in which all the planets orbit our sun. This is a finding that sends a chill down the spine of any cosmologist. It suggests one of two deeply unsettling possibilities. The first and more conservative explanation is contamination. Perhaps the signal we are interpreting as a message from the dawn of time is being corrupted by something much closer to home, dust in our own solar system, or some other local foreground we have not yet accounted for, could be imprinting this specific pattern onto the data. If true, it means we are not looking at a pristine cosmic signal but a distorted one, like trying to listen to a faint symphony while standing next to a humming generator. The second possibility is far more profound. If the alignment is real, if it is a genuine feature of the cosmic microwave background, then it implies a connection so bizarre it defies comprehension. It would mean that the largest scales of the entire observable universe, the patterns laid down at the moment of creation, are somehow linked to the orientation of our tiny, insignificant solar system. This would be an astronomical coincidence on a level that shatters the Copernican principle, the idea that we do not occupy a special place in the cosmos. It would suggest that our local neighborhood is, in some inexplicable way, woven into the fundamental fabric of the universe. This potential for contamination forces a critical question. How much of what we see is truly the universe, and how much is just a reflection of our own backyard? The unsettling link between our solar system and the cosmic blueprint forces a difficult question of perspective. Could other anomalies simply be illusions created by our own vantage point? The next pattern suggests the distortion is real and far more fundamental. The universe itself appears to be lopsided. When scientists measure the strength of the temperature fluctuations in the cosmic microwave background, they find a startling imbalance. One half of the sky is inherently more dramatic than the other. In one hemisphere, the hot and cold spots are more pronounced, their contrast sharper and more powerful. The other hemisphere is comparatively muted, its variations softer and less extreme. This is the hemispherical power asymmetry, and it is a profound violation of cosmic fairness. The universe, it seems, did not start with a level playing field. The principle of isotropy demands that the cosmos should look statistically identical in every direction. There should be no special hemisphere, no cosmic north or south that exhibits fundamentally different properties. This asymmetry is like flipping a coin billions of times and finding that it consistently lands with more force when thrown toward the east. The pattern is not a local smudge or a single cold spot. It is a global preference written into the very fabric of the primordial universe. Some theorists describe it as a dipolar modulation, a gentle wave of influence that made the early universe slightly hotter and more variable on one side and cooler and calmer on the other. But what could generate such a wave? What physical process could impose a gradient on the entire Big Bang? The answer is a complete mystery. This is not a flaw in the data, but a flaw in our foundational story. It suggests the initial conditions of creation were not simple and uniform, but incredibly complex and perhaps even biased. The seeds for all structure were not sown evenly across the cosmos. One side of the universe was simply given a head start. If the universe is not isotropic, then our entire understanding of its birth requires a radical rewrite. The next set of patterns pushes this idea even further, challenging not just the uniformity of space, but the fundamental randomness of time itself. The idea of a lopsided universe, where one half is inherently more dramatic than the other, challenges our most basic assumptions about creation. But the anomalies reach even deeper into the very nature of randomness itself. The standard story of the Big Bang's aftermath relies on a specific kind of chaos, a predictable disorder known as a Gaussian distribution. Imagine the static on an old television screen. The pattern of black and white dots is utterly random, but it follows a strict statistical rule. If you analyze it, you will find that extreme deviations, like a large, perfectly black square, are incredibly rare. The patterns are random, but their randomness has a predictable shape, a bell curve. Cosmologists have long assumed the tiny quantum ripples that became the cosmic microwave background followed this same Gaussian rule. It is the simplest and most elegant outcome of the rapid expansion known as inflation. Yet, as our maps of the ancient sky have grown more precise, a haunting question has emerged. What if the universe's randomness is not perfectly random? Meticulous searches through the temperature variations have hinted at possible deviations from this Gaussian ideal, a phenomenon called non-Gaussianity. This would mean the distribution of hot and cold spots is not quite what we expect. Perhaps there are too many extreme hotspots clustered together, or maybe the fluctuations are subtly correlated in ways that defy the bell curve. Finding significant non-Gaussianity would be a monumental discovery. It would be like analyzing the static on that television and finding hidden, repeating shapes within the noise. Such a finding would immediately rule out many of the simplest and most popular models of cosmic inflation. It would tell us that the physics of the universe's first fraction of a second was far more complex and exotic than we imagined. Perhaps inflation was not a single, smooth event, but involved multiple fields of energy interacting, or even collisions between different realms of spacetime. While the evidence is not yet conclusive, even the hints are powerful enough to drive theoretical physicists to develop increasingly elaborate models. The search for a flaw in the universe's randomness leads us to scrutinize even finer details, to the point where we must ask if the very geometry of space is an illusion. These strange statistical whispers converge most powerfully in the universe's largest features, the low multipole moments, which describe the grandest patterns of hot and cold stretching across the sky, are where the anomalies gather like storm clouds. It is here that the cosmic blueprint shows its most significant deviations from expectation. The quadrupole moment, the fundamental four-lobed pattern of the infant cosmos, is strangely quiet. Its power, the intensity of its temperature variations, is significantly weaker than our best models of the universe predict. According to the standard cosmological story, such a muted quadrupole is a statistical fluke of incredibly low probability. It is like rolling a pair of dice and getting a 2 100 times in a row. The universe, it seems, is whispering when it should be shouting. This is not a minor discrepancy. The quadrupole represents the largest possible waves in the fabric of the early universe, the foundational rhythms from which all smaller structures were born. Its surprising lack of power suggests that the cosmos may be inherently calmer on its very largest scales than our physics can account for. This quietude forces a profound question. Is this just an improbable but harmless coincidence, a lucky roll of the cosmic dice that means nothing? Or is it the first, faint signal that our understanding of the universe's infancy is fundamentally flawed? Perhaps the story of cosmic inflation, that brief period of hyperexpansion, was far more complex and turbulent than our simple models suggest. Maybe the universe's birth was not a smooth, uniform event, but a chaotic process that left the largest scales of reality strangely subdued. The anomalies etched into these large angles challenge the very notion of a serene and predictable beginning, but the mysteries are not confined to abstract statistics. The cosmic microwave background holds even more bizarre features, specific shapes that stare back at us from the depths of time. Perhaps the strangest pull on our universe comes not from within, but from beyond the edge of all we can see. This is the mystery of the dark flow. Unlike the temperature patterns we have discussed, this phenomenon is not a direct feature of the cosmic microwave background's heat map. Instead, it is a ghostly motion revealed by studying how the CMB interacts with the largest structures we know. Astronomers observed hundreds of massive clusters of galaxies, each containing thousands of galaxies, and measured their peculiar velocity, their movement relative to the overall expansion of the universe. They expected these motions to be random, a chaotic drift caused by the gravitational tug of neighboring superclusters, but the data revealed something astonishing. These colossal clusters are not drifting aimlessly. They appear to be streaming in a coherent direction, a vast river of galaxies flowing toward a specific point in the distant sky. This motion is detected through a clever technique called the kinetic Sunyaev-Zeldovich effect. As the light from the cosmic microwave background passes through the hot gas within a galaxy cluster, the motion of that cluster imprints a tiny, telltale shift on the light's temperature. It is like hearing the faint Doppler shift in a siren as an ambulance moves, but applied to the oldest light in the universe. The staggering implication is that this coordinated motion cannot be explained by anything within our observable universe. The gravitational pull from all the visible matter we have mapped is not nearly strong enough to create such a coherent stream. This suggests a radical possibility. Something immense and utterly unknown, lying far beyond the cosmic horizon of 14 billion light-years, is exerting a gravitational pull on everything we can see. It is as if we are living on a shore and all the driftwood is being pulled by a tide whose source is a continent over the horizon. If the dark flow is real, it means our universe is not an island. The structures and forces we consider to be everything are merely a local neighborhood, subject to influences from a greater cosmos we cannot yet perceive. This concept forces us to confront the ultimate limit, the final veil that may forever separate us from the true totality of existence. This gravitational tide, the dark flow, hints at forces beyond our horizon. But a more subtle effect, one woven into the very fabric of the cosmic background itself, suggests a flaw in our understanding of the forces we think we know. It is called the integrated Sachs-Wolfe effect. To grasp its anomaly, we first need to understand the journey of a single photon of ancient light. After it was freed during recombination, this photon spent billions of years traveling across an expanding universe. It sailed through vast cosmic voids and passed near immense superclusters of galaxies. Each of these structures has a gravitational field, a well in the fabric of space-time. According to Einstein's theory, as light climbs out of a gravitational well, it loses energy, causing its wavelength to stretch slightly toward the red end of the spectrum. This is a well-understood phenomenon. The integrated Sachs-Wolfe effect adds a crucial twist. It occurs because the universe is not static. It is expanding at an accelerating rate, driven by the mysterious force we call dark energy. This acceleration causes the gravitational wells of large-scale structures to change over time. As a photon enters a supercluster, the well may have been deep. But as the photon travels through it, the well becomes shallower because dark energy is pushing the universe apart, diluting the cluster's gravitational pull. The photon loses energy climbing into the well, but it gains less energy climbing out because the well has become less steep during its journey. The net result is a tiny, additional shift in the photon's energy. This integrated effect, accumulated over billions of light years, leaves a specific imprint on the cosmic microwave background. It should create very subtle, cold spots where light passed through evolving superclusters and warm spots where it passed through evolving voids. Scientists have indeed detected this signal. The problem is, it is too strong. The observed effect is more pronounced than our models predict based on the measured distribution of galaxies and the presumed strength of dark energy. This discrepancy is a quiet but powerful alarm bell. It suggests one of two possibilities. First, our understanding of dark energy might be wrong. Perhaps it is not a simple, constant force, the cosmological constant represented by lambda in our lambda CDM model. Maybe dark energy evolves, growing stronger or weaker over time, which would alter how quickly gravitational potentials decay and thus amplify the integrated Sachs-Wolfe signal. The second, equally troubling possibility is that our census of the universe's large-scale structure is fundamentally flawed. Perhaps there is more matter, or it is clustered in a different way than our galaxy surveys have revealed. Either way, this anomalous effect is not a minor statistical glitch. It is a direct measurement that reveals a disconnect between the growth of the largest structures in the universe and the behavior of the energy that dominates it. This subtle whisper from ancient photons tells us that the dominant forces shaping cosmic destiny are not yet fully understood. The elegance of inflation now faces its most severe test. This theory, born to explain the universe's large-scale smoothness, is being challenged by the very data it sought to clarify. The quiet quadrupole and the missing correlations on vast scales are not minor puzzles. They are fundamental inconsistencies that the simplest versions of inflation cannot easily overcome. To salvage the theory, cosmologists have ventured into increasingly complex territory. Perhaps the initial hypersurface of the universe was not flat but subtly curved, like the surface of a gentle hill, which would naturally suppress the largest waves. Or maybe inflation was not a single, continuous burst. It could have been interrupted, starting and stopping in a way that left the grandest patterns muted. Yet these solutions often feel like patches on a fraying fabric. They require a level of fine-tuning that begins to mirror the problems they aim to solve, introducing special conditions that seem just as improbable as the anomalies themselves. This growing tension forces a radical question: could inflation be wrong? The search for answers has led some physicists to consider entirely different origin stories for the cosmos. Perhaps our universe is cyclic, undergoing an endless sequence of big bangs and big crunches. Or maybe it emerged from a bounce, a previous phase of contraction that reversed into our current expansion. These ideas are not yet mainstream, but the persistent anomalies in the cosmic microwave background give them a compelling reason to exist. They represent the necessary friction that drives science forward, the undeniable data points that refuse to fit neatly into our established picture. And if the story of our beginning is flawed, what then of its end? The next patterns we uncover may not be from the dawn of time, but from a time before the dawn. The quiet anomalies we see might not be flaws in the universe, but flaws in our perception of its true size and shape. We naturally assume space is infinite and simply connected, a vast, featureless stage stretching forever. But what if the stage is finite and folded in on itself? This is the radical idea of cosmic topology. The universe could have a non-trivial shape, a global architecture that loops back around like a cosmic hall of mirrors. In such a world, if you could travel in a perfectly straight line for long enough, you would not journey into an endless void. You would eventually return to your starting point, just like an ant walking on the surface of a sphere. The observable universe, the 14 billion light-year horizon from which light has had time to reach us, would be merely a small patch on this larger, looping structure. The most profound signature of this would be etched into the cosmic microwave background. Because the universe wraps around, the ancient light from the Big Bang could have taken multiple paths to reach us. It might have traveled a short, direct route and also a much longer, looping route around the entire cosmos. When we look at the CMB map, we would therefore see the same pattern of hot and cold spots appearing in two different places on the sky. These would be matched circles, pairs of regions with an identical temperature pattern, like a celestial fingerprint repeated. Finding just one pair of these correlated circles would be a discovery of monumental importance. It would prove that the universe is finite and reveal its precise geometric form. Is it a three-dimensional torus, a hyperdimensional donut? Is it a more complex shape, a dodecahedron whose faces connect in strange ways? The search for these ghostly echoes is incredibly difficult. Scientists have scanned the cosmic microwave background for any sign of matching patterns, but the results have been inconclusive. The circles, if they exist, may be too faint or too large for our current telescopes to resolve. Or perhaps the universe is simply so vast that its repeating patterns lie just beyond our observable horizon. Yet the possibility remains deeply compelling. It transforms the cosmos from an endless expanse into a defined object with a specific shape. The search for cosmic topology is not just about finding circles in the sky. It is a search for the universe's hidden blueprint, the ultimate architectural plan of reality itself. Yet the search for the universe's shape is far from settled. The geometry of the cosmos is measured in two distinct ways, and they are whispering different stories. The cosmic microwave background provides our most powerful evidence for a flat universe. The patterns of hot and cold spots, their specific sizes and distributions, act like a cosmic ruler. In a curved universe, this ruler would be distorted. Light would travel along bent paths, making large features appear different than they truly are. The CMB data, however, shows no such distortion. It points to a universe that is geometrically flat to an astonishing degree of precision, like a perfectly stretched sheet. This finding is a cornerstone of our standard model of cosmology. But when astronomers use other methods to measure the universe's curvature, a subtle tension emerges. Techniques like observing how light from distant galaxies is bent by gravity, a phenomenon called gravitational lensing, or by meticulously mapping the large-scale clustering of galaxies, sometimes suggest a universe with a very slight positive curvature. This would mean space is not perfectly flat but closed like the surface of a sphere. The discrepancy is tiny, still hovering within the margins of error of our observations. It is a whisper, not a shout, but in the precise science of cosmology, even a whisper can be deafening. A genuinely closed universe would be a revolution. It would mean the cosmos is finite, having a definite volume without any edge. If you traveled far enough in a straight line, you would eventually loop back to your starting point. Such a geometry would also dictate a different ultimate fate, one where the current expansion eventually halts and reverses into a great collapse. This curvature tension is a reminder that our understanding of the cosmos is built on a delicate balance of measurements. When two different ways of looking at the universe fail to perfectly agree, it signals that a fundamental piece of the puzzle may be missing. This search for consistency leads us to question the very bedrock of physics, the seemingly immutable numbers that govern reality itself. The most unsettling anomalies are not in the patterns we see, but in the potential cracks in reality's rulebook. This leads us to a hypothesis so profound it questions the very stability of the cosmos. What if the laws of physics are not the same everywhere? Some theories propose that a number so fundamental we consider it a constant, the fine structure constant known as alpha, might actually be changing. Alpha governs the strength of the electromagnetic force, the glue that holds atoms together and dictates how light and matter interact. If alpha were different, the entire chemical universe would change. The strength of chemical bonds, the very colors of light that atoms absorb, all of it would shift. While this is not a pattern we directly observe in the cosmic microwave background, a varying alpha would have left a clear fingerprint on it. It would alter the precise balance of the acoustic peaks, those frozen sound waves in the early plasma. A different alpha would mean a different stiffness to the primordial fluid, changing the relative heights of those peaks in a specific, detectable way. Scientists have used the exquisite data from the Planck satellite to hunt for this signature. So far, they have found nothing. The data places incredibly tight constraints on how much alpha could have varied, effectively ruling out the simplest models that propose dramatic changes. But the door is not completely closed. The mere possibility that our physical constants are not eternal anchors, but could be more like local customs in a much larger and more varied cosmos, is a tantalizing thought that fuels continued research. This idea connects to a deeper concept, a vacuum that is not empty but dynamic, whose properties might evolve over cosmic time. If the constants can change, then the universe is not just expanding, it is fundamentally transforming. The most profound mysteries of our universe are not the stars and galaxies we see, but the invisible forces that orchestrate them. We have given these forces names, dark matter and dark energy, yet we know almost nothing about their true nature. Our entire cosmological model is built on a critical assumption that these two dark components are entirely separate, passing through each other without a whisper of interaction. Dark matter pulls, gathering to form the gravitational scaffolding for galaxies. Dark energy pushes, driving the expansion of space itself. They are the cosmic yin and yang, one building structure, the other stretching it apart. But what if this fundamental division is an illusion? The idea that dark matter and dark energy might interact is a heresy against the standard model, yet it is a heresy that could solve several puzzles at once. If these two entities could exchange energy, the entire history of cosmic evolution would change. In the early universe, such an interaction would have subtly altered the growth of the very first structures. It would have left a unique fingerprint on the cosmic microwave background, a slight distortion in the precise pattern of the acoustic peaks, those frozen sound waves from the Big Bang. The peaks would be shifted, their heights and spacing telling a different story about the balance of forces in the cosmos's infancy. So far, our most precise maps from the Planck satellite show no evidence for this interaction. The data is perfectly consistent with two separate, non-communicating shadows. But the absence of evidence is not evidence of absence. Our current measurements are like listening to a complex symphony with ears that are not quite sharp enough to detect a single instrument playing slightly out of tune. The next generation of observatories, like the European Space Agency's Euclid telescope, will listen with far greater sensitivity. They will measure the shapes and distributions of billions of galaxies, tracing the invisible hand of dark matter with unprecedented detail. If there is even a faint coupling between the dark sectors, these new eyes on the cosmos will find its signature. Discovering such an interaction would be more than just a new piece of physics. It would be a revolution. It would mean that 95% of the universe's content is governed by a single, unified, and utterly unknown physics. Instead of two separate mysteries, we would be facing one colossal enigma. This possibility pulls our gaze back to the very beginning, to a time when these dark components were not just interacting, but may have been born from the same primordial event. Magnetic fields are the silent architects of the cosmos, shaping the birth of stars and the spiral arms of galaxies. But their origin story is a profound mystery. Could they have been present at the very beginning, woven into the fabric of the universe in its first moments? This question leads us to one of the most subtle and challenging patterns hidden within the cosmic microwave background, a ghostly signature in the light's polarization. Light can vibrate in different directions, a property we call polarization. The cosmic microwave background is polarized in a specific way, a direct result of photons scattering off electrons in the hot plasma of the infant universe. Most of this polarization is a simple pattern, like the ripples spreading out from a stone dropped in a pond, but theorists predict another, far more elusive type. It is a curling pattern, a faint swirl in the polarization map known as B-mode polarization. This curl is the holy grail for cosmologists searching for primordial magnetic fields. The idea is staggering. If vast magnetic fields permeated space before the first stars ever ignited, they would have gently twisted the polarization of the ancient light as it traveled through the primordial plasma. Finding this swirl would be like discovering the fossilized footprint of a force that shaped the cosmos from its very first breath. the implications would be monumental. Such fields could not have been created by early stars or galaxies because they would have existed before any structure formed. Their presence would point to physics at energy scales we can only dream of, perhaps generated during violent phase transitions in the universe's infancy, when the fundamental forces of nature themselves were splitting apart. Yet, this definitive swirl has not been found. Our most sensitive telescopes have only been able to place an upper limit on its strength, telling us how weak these primordial fields must be if they exist at all. But even this non-discovery is a powerful clue. It acts as a strict constraint, ruling out entire classes of theoretical models about the universe's hyper-energetic birth. The search for this magnetic imprint is more than a hunt for a pattern. It is a direct probe into an era forever hidden from particle colliders, an era where the laws of physics as we know them were being forged. This polarization is a whisper within the ancient light, a subtle directionality imprinted on the cosmic glow. To understand its deepest secret, we must learn its language, a language of two distinct patterns known as E modes and B modes. Think of the primordial plasma as a vast, simmering ocean. The density fluctuations, the hills and valleys of matter, create waves that push and pull on the fabric of space. When light scatters off electrons in this churning fluid, it becomes polarized in a specific, straightforward way. This creates the E-mode pattern. It is a radial pattern, like the straight lines emanating from a point of high pressure, or the petals of a flower arranged in perfect symmetry. These E-modes are a direct consequence of the density variations we see in the temperature map, and they are beautifully explained by our standard models. They are the expected signature of a chaotic birth. The B modes, however, are a different story entirely. They are the curl, the swirl in the polarization map. Instead of straight lines, imagine the gentle, rotating patterns of water circling a drain. This curling signature can be created by two profoundly different cosmic events. The first source is gravitational lensing. As the ancient light from the CMB travels for billions of years, its path is bent by the gravitational fields of all the matter it passes, from dark matter halos to giant clusters of galaxies. This cosmic distortion can twist the simple E-mode polarization, stretching and warping it into a secondary, faint B-mode pattern. This lensing signal has been detected, and it serves as a powerful map of the universe's total matter distribution. But the second potential source of B modes is the true prize, a signal so faint it has become a legendary quest in cosmology. These are the primordial B modes, generated in the first fleeting instance of the universe by gravitational waves from inflation itself. Inflationary theory predicts that the violent, hyper-fast expansion of space should have generated ripples in the very fabric of space-time, gravitational waves that would have polarized the primordial plasma in a unique, curling pattern. Finding this specific B-mode signal would be like hearing the echo of the Big Bang's first shudder, a direct observation of quantum gravity in action. It would provide incontrovertible proof that inflation occurred and open a window into energy scales 1 trillion times higher than what our particle colliders can achieve. Yet, despite decades of searching with increasingly sensitive telescopes deployed at the most remote and pristine locations on Earth, this definitive signal has not been found. Its absence is deafening. The level of the signal is far fainter than the most optimistic early models of inflation predicted. This non-detection is not a failure, it is a ruthless editor. It has already ruled out whole families of the simplest and most elegant inflationary theories. The universe, it seems, did not begin with a dramatic, roaring tremor, but with a whisper too soft for us to yet hear. The relentless search for this curl continues, pushing the boundaries of technology. because the reward is nothing less than understanding how everything began. Even the ghostly imprint of gravitational waves is not the final whisper from the ancient light. A more subtle distortion, one that warps the universe's baby picture itself, reveals another crack in the model. This is the lensing amplitude anomaly, a discrepancy in how the cosmos bends its own oldest light. Gravitational lensing is a cosmic phenomenon we see everywhere. The gravity of any massive object, from a single galaxy to a vast cluster, acts like a lens in space, warping the fabric of space-time and bending the path of light that travels through it. This effect does not just apply to light from distant galaxies, it also distorts the cosmic microwave background. As the ancient photons journey toward us for over 13 billion years, their paths are gently twisted and magnified by the gravitational pull of all the matter they pass. This cosmic lensing subtly smears the pristine temperature patterns of the CMB, smoothing out the sharpest peaks and valleys in a specific, measurable way. The amount of this smearing, called the lensing amplitude, should perfectly match the amount of structure we have mapped in the universe. Our standard model, calibrated with exquisite precision by the Planck satellite, makes a very specific prediction. But the universe has delivered a different answer. When scientists measure the lensing effect directly from the CMB maps, they find it is slightly stronger than expected. The observed smearing is about 10% more pronounced than the model predicts. This might sound like a small difference, but in the world of precision cosmology, it is a significant and persistent tension. It is as if we are looking at a photograph through a slightly more powerful magnifying glass than we thought we had. This anomaly suggests one of two intriguing possibilities. First, it could mean there is simply more stuff out there, more dark matter and galaxies weaving a denser gravitational web than our current surveys have accounted for. The universe might be slightly more clumpy on large scales, enhancing the lensing effect. The second, more radical idea is that the properties of the invisible components themselves are not what we assume. Perhaps dark matter has a small interaction we have not considered, or maybe neutrinos, the ghostly particles that flood the cosmos, are more massive than we think. Either of these could alter how cosmic structures grow, and in turn how strongly they bend the light from the dawn of time. This lensing anomaly is a quiet clue, a faint suggestion that our census of the cosmic landscape and the rules governing its growth may still be incomplete. This single number, the Hubble constant, is more than just a measurement. It is the master dial for the age, size, and ultimate fate of our entire cosmos. And right now, that dial is giving us two different readings. The crisis is this: when we measure the universe's current expansion rate using our most reliable cosmic yardsticks, like the pulsing rhythm of Cepheid variable stars and the brilliant flash of Type 1, a supernova, we get one answer. This is the local measurement, a snapshot of how fast galaxies are rushing away from us in our cosmic neighborhood. It is a direct, empirical reading of the present-day universe. But when we use the cosmic microwave background as a time capsule, we get a completely different story. The intricate pattern of hot and cold spots in that ancient light allows us to run the cosmic film in reverse. By plugging the initial conditions of the Big Bang into our standard model of cosmology, we can predict exactly how fast the universe should be expanding today. This prediction, based on the physics of the infant cosmos, gives us a Hubble constant that is significantly lower. The two values do not match. They are separated by a gap that cannot be explained by measurement errors. It is as if you calculated how fast a car should be going based on the power of its engine and the incline of the road, only to look at the speedometer and find it is moving noticeably faster. Something is wrong with your understanding of the car, or the road, or both. This Hubble tension is not a minor discrepancy. It is a 5 sigma level problem, a statistical threshold that in particle physics would be declared a definitive discovery. It screams that our standard model of cosmology, the lambda CDM model that has guided us for decades, is incomplete. It is missing a crucial piece of physics. The question is, what is that piece? Theorists have proposed a zoo of possibilities. Perhaps dark energy is not a constant force but an evolving one that has grown stronger in recent cosmic history, giving the expansion an extra kick. Or maybe dark matter possesses some strange, unknown property that alters how structures form and thus changes the calibration from the early universe to today. There is even the radical suggestion that the early universe was somehow different, perhaps cooler or with a different balance of radiation, which would throw off the prediction derived from the cosmic microwave background. Each proposed fix tries to bend the model to make the early and late universe agree, but so far, no solution has gained widespread acceptance without creating new problems elsewhere. This persistent tension is a powerful engine for discovery, forcing cosmologists to question their most basic assumptions about the dark components that make up 95% of the universe. It is a direct challenge written in the expansion of space itself, telling us that the story we have written for the cosmos is still missing a fundamental chapter. But the Hubble constant is not the only dial giving a contradictory reading. A second, equally profound tension lurks within the data, a discrepancy in the very texture of the cosmos. This is the story of the S8 tension. If the Hubble constant measures the speed of the universe's expansion, then S8 measures its roughness, the degree to which matter has clumped together to form the vast cosmic web of galaxies and voids we see today. The cosmic microwave background provides a prediction for this clumpiness. The precise pattern of the ancient light's temperature variations tells us exactly how much gravitational seed was planted in the universe's infancy. Running the cosmic simulation forward, our standard model predicts how those tiny seeds should have grown over 13 billion years into the grand structures of the present day. It gives us a specific number for S8, but when astronomers go out and actually measure the universe's current clumpiness using a powerful technique called weak gravitational lensing, they get a different answer. This method does not rely on a prediction. It takes a direct census. By observing how the light from millions of distant galaxies is subtly distorted as it passes through the gravitational fields of intervening dark matter, scientists can create a three-dimensional map of the cosmos's matter distribution. The result is clear. The real universe appears to be slightly smoother, less clumpy than the one predicted by the CMB. The difference is small, but like the Hubble tension, it is persistent and statistically significant. It is as if we planted a field based on a detailed blueprint, expecting a landscape of sharp hills and deep valleys, but instead found a terrain of gentler, more rounded mounds. The S8 and H0 tensions together form a 1-2 punch against our standard cosmological model. One tells us the universe is expanding too fast, the other tells us it is not lumpy enough. A problem with a single parameter could be a fluke, but two independent anomalies point to a more fundamental flaw. They suggest that the lambda CDM model, for all its breathtaking success in describing the universe's evolution, is beginning to show its age. The pristine data from the early universe no longer perfectly aligns with the direct observations of our cosmic present. This growing rift hints that the simple story of dark matter and a constant dark energy may be missing a crucial chapter, a dynamic interaction or an unknown property that alters the cosmic recipe between then and now. These tensions in our cosmic model are not confined to the grand scales of expansion and structure. They echo down into the specific interactions between the ancient light and the universe that grew from it. This brings us to the ghostly shadow cast by galaxy clusters, known as the thermal Sunyaev-Zeldovich effect. Imagine the cosmic microwave background as a uniform, cold backlight shining through the entire cosmos. When this ancient light passes through a massive galaxy cluster, it does not travel through empty space. It plunges through a sea of incredibly hot gas, a plasma of electrons with temperatures reaching millions of degrees. As the cold CMB photons collide with these energetic electrons, they receive a tiny kick, a boost in energy. This interaction scatters the photons, slightly shifting their frequency and creating a specific, predictable distortion in the background light. Instead of a cold spot, the cluster leaves a faint, warm shadow. This is not a temperature change we can see with our eyes, but a distinct signature that specialized telescopes can detect across different wavelengths. It is a direct way to find the most massive structures in the universe, simply by seeing how they dimple the oldest light. The power of this effect lies in its simplicity. It depends only on the pressure of the hot gas within the cluster, not on how far away the cluster is. But here is where the anomaly emerges. When scientists measure the combined strength of this effect from all the clusters across the sky, creating a statistical power spectrum, the signal is quieter than it should be. The universe's clusters seem to cast a fainter shadow than our best cosmological simulations predict. It is as if the hot gas within these giant clusters is less energetic, or perhaps there are fewer very massive clusters than we thought. This discrepancy points a finger at two very different possibilities. The first is astrophysical. Perhaps our understanding of the inner workings of galaxy clusters is flawed. The supermassive black holes at the centers of galaxies pump vast amounts of energy into their surroundings through powerful jets, a process called active galactic nucleus feedback. This feedback could be heating the cluster gas more effectively than our models account for, making it puffier and less dense, which would weaken the Sunyaev-Zeldovich signal. The second possibility is far more profound. What if the anomaly is not about the gas, but about the gravitational glue that holds the clusters together? If dark matter has properties we have not anticipated, perhaps a form of interaction that subtly affects how clusters form and retain their hot gas, it could explain why the observed signal does not match our expectations. This faint whisper from the heated gas of clusters is a crucial link. It ties the pristine physics of the Big Bang directly to the messy, complex astrophysics of the universe that came after. A small anomaly here forces us to question everything from the violent life cycles of black holes to the fundamental nature of the invisible matter that shapes our cosmos. The faint warmth of a galaxy cluster's shadow is only one way it interacts with the ancient light. As the cosmic microwave background passes through these colossal structures, a far more subtle effect takes place, revealing not just the presence of matter, but its motion through the cosmos. This is the kinetic Sunyaev-Zeldovich effect. While the thermal effect gives the photons an energy boost from hot electrons, the kinetic version is far more ghostly. It occurs when the entire cluster of galaxies is moving as a single unit, drifting with a coherent velocity relative to the overall expansion of the universe. The electrons within the cluster's hot gas are carried along with this bulk flow. As a cold CMB photon scatters off one of these moving electrons, its frequency is shifted ever so slightly, in a way that depends purely on the cluster's speed and direction. It is the cosmic equivalent of the Doppler shift you hear in a passing siren, but applied to the oldest light in existence. By meticulously measuring this tiny imprint across thousands of clusters, cosmologists can map the velocity flows of matter on the largest scales imaginable. They can trace the great rivers of the cosmic web, the bulk motions where vast collections of galaxies stream together in a shared direction. According to our standard story of structure formation, these flows should have a very specific origin. They should be driven entirely by gravity, the relentless pull of surrounding dark matter halos tugging these clusters into motion. This is the gravitational instability picture, and it makes precise predictions about how fast these bulk flows should be and how they should be distributed across the sky. But what if the maps reveal something else? If the measured velocities are consistently stronger or more coherent than gravity alone can explain, it would point to a startling possibility. The seeds for these massive motions may have been planted in the universe's first moments. Instead of the smooth, adiabatic fluctuations that inflation typically produces, the early cosmos might have been seeded with what theorists call isocurvature perturbations. These are initial ripples not in the total energy density, but in the ratio of different components, like the balance between matter and radiation. Such a different starting point could have set up peculiar large-scale flows from the very beginning, flows that gravity alone cannot account for. The kinetic Sunyaev-Zeldovich effect turns the cosmic microwave background into an immense screen, and the moving clusters of galaxies into celestial projectors, casting shadows that tell the story of the universe's deepest currents. Any anomaly in their motion is a whisper from a time before structure, a hint that the initial conditions of everything were even more complex than we dreamed. Even the pristine uniformity of the cosmic background holds a secret vulnerability. We have been reading its story through temperature and polarization, but the light itself has another dimension, its color. The cosmic microwave background is the most perfect blackbody in the universe, a glowing object whose color spectrum is defined solely by its temperature. This perfect curve is a direct consequence of the universe's hot, dense beginning. Yet, this perfection is a facade that could be cracked. If any violent event had injected a burst of energy into the cosmic plasma after its initial formation, but before the first stars lit up, it would have left a permanent scar on the light's color, a subtle deviation known as a spectral distortion. These distortions are not patterns on the map, but ghosts in the machine of the light itself. One type, called the Y distortion, would be a telltale sign of a relatively late energy injection. Imagine the ancient cosmic gas being gently warmed, perhaps by the collective heat from the first proto-galaxies, or even by the decay of an exotic form of dark matter. This warming would give the cold background photons a slight energy kick, subtly altering the perfect blackbody curve in a specific way. An even more profound signal would be a mu distortion. This fingerprint points to a much earlier cataclysm, a violent energy release occurring in the cosmic dark ages, a period spanning from about 3 months to 300,000 years after the Big Bang. During this era, the universe was a silent, expanding fog of hydrogen and helium, too young for stars and too old for its own light to carry a detailed memory of its birth. If a massive event, like the annihilation of primordial black holes or the decay of unknown particles, had dumped energy into this fog, the physics of how that energy was absorbed would have created a unique mu distortion. These spectral fingerprints are incredibly faint, so faint that our current observatories have not detected them. But the hunt is on. Proposed missions like the Primordial Inflation Explorer, or PIXIE, are designed with the sole purpose of measuring the cosmic microwave background spectrum with mind-boggling precision. Finding even the tiniest deviation from the perfect blackbody curve would be like discovering a fossilized explosion from a time before time, a direct message from the universe's most silent and mysterious epoch. It would open a window into the Dark Ages, a chapter of cosmic history we have never before been able to read. This whisper from the Dark Ages connects to a ghost that permeates all of space, a particle so elusive it can pass through light years of lead without a trace. The cosmic microwave background carries a subtle imprint of neutrinos, and this imprint places a strict limit on their mass. In the fiery first second of the universe, neutrinos were not the slow, massive particles we try to detect today. They were relativistic, moving at nearly the speed of light. This meant they could fly freely across the primordial plasma, an effect cosmologists call free streaming. As they streamed, these countless ghostly particles acted like a cosmic smoothing iron, their relentless motion damping down the growth of the smallest ripples in the density of the universe. They suppressed the formation of the tiniest structures. This damping leaves a specific signature in the detailed power spectrum of the CMB, a slight smoothing of the acoustic peaks on smaller scales. By measuring this smoothing with incredible precision, scientists can work backwards to calculate the total gravitational influence of all neutrinos combined. The result is a remarkably tight constraint. The combined mass of all three known types of neutrinos must be less than about 0.12 electron volts. To put that in perspective, this is more than 1,000,000 times lighter than the electron, the next lightest particle we know. This cosmic measurement is now so precise that it is beginning to clash with hints from particle physics experiments. Some experiments suggest neutrinos might follow what is called an inverted mass hierarchy, where the two heavier neutrinos are very close in mass and the lightest one is far lighter. This arrangement would require a total mass that is now perilously close to, or even exceeding, the limit set by the cosmos. The universe's baby picture is therefore doing more than just telling us about its own birth. It is acting as a colossal particle detector, ruling out possibilities for the fundamental building blocks of reality. The silent film of the CMB is whispering secrets about the smallest things in existence, forcing a conversation between the science of the immense and the science of the infinitesimal. The universe's silent dark ages ended in a blaze of creation. After hundreds of millions of years of darkness, the first stars ignited, their fierce ultraviolet light flooding the cosmos. This was the epoch of reionization, a pivotal moment when the fog of neutral hydrogen that had filled the universe was blasted apart, its atoms torn back into free electrons and protons. The cosmic microwave background carries a faint, frozen memory of this great awakening, not in its temperature but in its polarization. The scattering of light during this second clearing of the cosmic fog imprinted a specific, large-scale pattern. The strength of this signal is measured by a single, crucial number called the optical depth, represented by the Greek letter tau. This number tells us how opaque the universe was to this rescattered light, essentially timing the reionization event. And this number has become a quiet battleground between two different ways of seeing the cosmos. Early data from the Planck satellite suggested a relatively high value for tau, implying that reionization happened surprisingly early, beginning when the universe was only a few 100 million years old. This was a problem for astrophysicists who modeled the formation of the first stars and galaxies. Their simulations struggled to produce enough brilliant, early objects to ionize the entire cosmos so quickly. It was as if we had found evidence of a massive, ancient civilization, but our archaeological records showed only a few scattered villages. Later, more refined analyses of the Planck data have slightly lowered the value of tau, pushing the reionization timeline a bit later and easing the tension. Yet the puzzle remains. The optical depth is a vital bridge, the only direct observational link we have between the pristine physics of the Big Bang and the messy, brilliant dawn of astrophysics. Getting its value right is essential for writing a consistent history of the universe. If our measurement is off, It means we do not truly understand how or when the lights first came on, a fundamental chapter in the story of everything. Our own motion through the cosmos should be the simplest thing to measure. The solar system's journey around the galactic center, the Milky Way's drift through the local group, all of these movements combine into a single velocity relative to the cosmic microwave background's rest frame. This motion creates a clear and expected signature in the ancient light, a phenomenon called the Doppler dipole. It is the universe's most basic temperature map, a pattern where the sky ahead of us appears slightly warmer, blue-shifted by our approach, while the sky behind is cooler, red-shifted by our departure. This dipole is the largest single feature in the entire CMB, and for decades it has been the ultimate anchor, the reference frame against which all other cosmic motions are defined. It is the baseline of our cosmic navigation, yet this foundation may be cracking when astronomers try to measure this same universal motion using a different method, by observing the distribution of incredibly distant quasars and radio galaxies. They get a result that does not quite match. These point sources, beacons from the far reaches of space, show a dipole of their own. The pattern of their numbers across the sky should, in theory, perfectly mirror the CMB dipole, revealing our motion through the same absolute frame. But some meticulous studies suggest a discrepancy. The dipole measured from these quasars seems to have a different amplitude, a different strength, and may even point in a slightly different direction. This is the point source dipole anomaly, and if it is real, the implications are staggering. It challenges the core principle that the cosmic microwave background defines the rest frame of the entire universe. What if the CMB rest frame is not universal after all? What if it is only a local phenomenon, the frame of our immediate cosmic neighborhood, while the wider universe has a different preferred state of rest? This would mean there is no single, absolute backdrop for reality. It is a radical suggestion that the very fabric of space might be moving on scales so vast we cannot yet comprehend them, dragging the CMB along with it like foam on a cosmic current. The debate is fierce, with many scientists arguing that the anomaly is a statistical fluke or an artifact of incomplete data. But the mere possibility forces a profound question. Are we truly measuring the universe's motion, or is the universe moving around us in ways we are only beginning to sense? These potential alignments stretch beyond our solar system's disk, reaching toward the very architecture of our home galaxy. A handful of studies have suggested that certain large-scale features in the cosmic microwave background might also show a strange preference for the plane of the Milky Way. This is an even more troubling prospect than the ecliptic alignment. Our solar system is a tiny speck within the galaxy, but the galaxy itself is a massive structure, a swirling disk of stars, gas, and dust. If the universe's oldest light carries an imprint of this local geometry, it would imply a contamination source of cosmic proportions. The primary suspect is foreground emission. Our Milky Way is not a silent backdrop. It is a brilliant source of light across many wavelengths. It glows with synchrotron radiation from electrons spiraling in magnetic fields, and it shines with thermal emission from vast clouds of interstellar dust. The scientists working on missions like Planck spend an enormous portion of their time building intricate models to subtract this foreground glare. It is like trying to listen for a faint, distant melody while standing in the middle of a roaring orchestra. The fear is that some subtle, unmodeled component of this galactic emission might be mimicking a cosmological pattern. Perhaps a faint, large-scale asymmetry in the galaxy's own magnetic field or dust distribution is leaving a ghostly smear on the data that we mistake for a primordial signal. There is also the more unsettling possibility of an instrumental systematic effect. The satellite itself, with its specific scanning pattern across the sky, could potentially introduce a very low level of artificial pattern that coincidentally aligns with a local plane. The teams behind these experiments perform heroic efforts to rule this out, but the possibility always lingers in the background of every claimed discovery. This is the ultimate test for any anomaly in the cosmic microwave background. Before we can declare a finding as evidence of new physics, we must prove beyond a reasonable doubt that it is not just a reflection of our own backyard or a quirk of the magnificent tool we use to capture the light. The true signal from the dawn of time must be isolated from the universe as it is today. This subtle preference for cosmic order runs even deeper, touching upon a fundamental symmetry we take for granted. The universe is supposed to be ambidextrous with no built-in preference for left or right-handedness. This principle, known as parity symmetry, is a cornerstone of physics. Yet, the cosmic microwave background seems to whisper of a universe with a favorite hand. When scientists decompose the ancient light's temperature map, they separate it into two distinct families of patterns, analogous to the E modes and B modes of polarization. These are called even parity and odd parity patterns. Think of even parity as a perfectly symmetrical design, like a snowflake where one half is a mirror image of the other. Odd parity, in contrast, is like a spiral staircase possessing a distinct handedness, a twist that cannot be superimposed on its mirror image. In a universe that respects parity symmetry, the statistical power, the intensity of these even and odd patterns should be perfectly balanced. They should be cosmic equals, but some detailed analyses of the largest scales suggest they are not. The odd parity patterns appear to be quieter, their power subtly suppressed compared to their even parity counterparts. It is as if the universe, at its birth, had a slight but noticeable preference for symmetrical designs over twisted ones. This odd parity preference is a statistical ghost, its significance still hotly debated among specialists. Is it just a fluke in the data, a random fluctuation amplified by our relentless search for patterns, or is it a real crack in the foundation of physics? If confirmed, it would mean that the principle of parity symmetry was violated not just in the laboratory, as it is for the weak nuclear force, but on a cosmic scale, woven into the fabric of the Big Bang itself. Such a discovery would force us to consider entirely new types of fields or particles that operated only in the universe's first instant, imprinting a fundamental bias onto the cosmos. The quiet struggle between even and odd patterns is a battle over the universe's most basic character, a hint that the laws of physics may have a preferred direction written into them from the very beginning. Even the faintest hints of non-Gaussianity would force a radical rethink of the universe's birth, but the search for this statistical ghost has grown even more sophisticated. The real prize may not be a single, uniform deviation from perfect randomness, but a signal that changes with the size of the features we observe. This is the idea of scale-dependent non-Gaussianity. Imagine listening to a vast, complex piece of music. The overall sound might seem harmonious, but a master musician could detect that the violins are slightly out of tune only during the slow movements, while the brass section falters in the crescendos. The flaw is not uniform, it is tied to the specific scale of the music's different sections. Cosmologists are listening to the symphony of the cosmic microwave background in exactly this way. They are not just asking if the universe's randomness is imperfect, but whether that imperfection has a specific fingerprint, a pattern that is stronger when looking at large patches of the sky and weaker on small scales, or vice versa. This subtle characteristic would be a game changer. It would act as a powerful filter, instantly ruling out broad classes of inflationary models while providing direct evidence for others. The simplest versions of inflation, which involve a single field of energy rolling smoothly down a gentle slope, tend to produce a non-Gaussian signal that is essentially the same across all scales. But the physics of the very first instant was likely far more dramatic. Some theories propose that the inflationary field encountered bumps or dips on its potential energy landscape. As it rolled over these features, its expansion would have stuttered or surged, creating sharp, localized bursts of non-Gaussianity that would imprint more strongly on specific angular sizes in the sky. Other models involving multiple fields interacting in a complex cosmic dance also predict a distinct scale dependence. Finding this specific signature would be like moving from knowing a crime was committed to finding the criminal's unique fingerprint at the scene. It would point directly to the specific type of particle physics that drove the universe's exponential growth, revealing the energy scales and the fundamental interactions that were in play during that fleeting, unimaginable moment. The hunt for this nuanced statistical whisper continues, pushing our day to analysis to its limits, because the reward is nothing less than identifying the engine of creation itself. The cold spot's mystery deepens when we look beyond its temperature to the very direction of its ancient light. To understand its polarization is to ask a critical question about its origin. If this frigid expanse were truly the shadow of a vast, empty supervoid, the light passing through it would carry a specific, predictable signature in its polarization. The gravitational decay of such a void, the process that would steal energy from the light, would also subtly align the light's vibrations in a particular way. It would be a clear, physical fingerprint left by a known phenomenon. Yet, when scientists meticulously measured the polarization patterns surrounding the cold spot, the expected signature was not there. The alignment of the light did not match the story a supervoid would tell. This mismatch is a quiet but devastating blow to the most straightforward explanation. It means the cold spot cannot be easily dismissed as a simple cosmic emptiness. The absence of the right polarization pattern forces the mystery to a more profound level. It transforms the cold spot from a potential illusion into a genuine feature of the primordial universe, an event frozen into the fabric of spacetime at the moment of its creation. This polarization anomaly has effectively closed one door, only to open others to far more speculative and thrilling possibilities. The cold spot is no longer just a cold spot. It is a unique laboratory, a cosmic puzzle box that invites us to test the most unconventional ideas physics can offer. Could it be the imprint of a cosmic texture, a defect in the structure of spacetime from the universe's first moments? Or is it the scar from a collision with another universe in the vast multiverse? Each of these exotic theories makes its own prediction about what the polarization should look like, and the strange data from the cold spot is the one piece of evidence against which they can be measured. The sheer number of strange patterns forces a difficult question. Are we witnessing profound new physics, or are we simply seeing ghosts in the data? This is the quiet battle over statistical significance that lies at the heart of all 48 anomalies. When you stare at a map as complex and detailed as the cosmic microwave background, the human brain is wired to find patterns. It is the same instinct that lets us see faces in clouds or animals in the stars. Cosmologists combat this bias with a mathematical shield, a rigorous set of tools designed to separate a true signal from a random fluke. The greatest enemy in this search is known as the look elsewhere effect. Think of it like rolling a pair of dice. If you roll them once and get 2 sixes, it is surprising but not impossible. Now imagine rolling those dice 1 trillion times. You are almost guaranteed to get a long sequence of double sixes somewhere in that vast dataset. The trick is to calculate the probability that such a sequence would appear by chance anywhere in all those rows, not just in one specific throw. For the cosmic microwave background, the look elsewhere effect is immense. Scientists test thousands of possible correlations, alignments, and asymmetries across the sky. By the pure laws of chance, some of them are bound to appear unusual. This is why the sigma value, the measure of statistical significance, is so crucial. A 5 sigma result is the gold standard in physics, indicating a mere 1 in 3.5 million chance that the finding is a random fluctuation. It is a declaration of discovery, but for the majority of these 48 patterns, the significance is far lower, hovering around 2 or 3 sigma. This translates to a 1 in 20 or 1 in 100 chance that the anomaly is just a statistical mirage. It is the scientific equivalent of a compelling whisper, a hint intriguing enough to keep you listening but too faint to be sure of what you heard. This ambiguity is why the cosmology community remains divided. For some, these whispers are the first cracks in a soon-to-crumble model. For others, they are distractions, mathematical phantoms that will vanish with more precise data. The resolution will not come from argument, but from a new generation of eyes on the cosmos. Future observatories, like the proposed CMB Stage 4 project, will map the ancient light with exponentially greater sensitivity and resolution. They will either elevate these whispers to a chorus of discovery, or they will silence them forever, forcing us to accept that the universe's blueprint is, after all, exactly as random as it seems. The battle to see the universe's first light is a fight against our own cosmic backyard. To isolate the pristine signal of the cosmic microwave background, scientists must perform a delicate operation, meticulously peeling away the brilliant glare of everything that lies between us and the edge of time. This process, known as foreground subtraction, is the unsung hero of modern cosmology, and its potential failures could be the source of many spectral ghosts. Our view is obscured by a fog of local emission. The Milky Way galaxy blazes across the sky with synchrotron radiation, a glow from electrons spiraling at near light speed within its magnetic fields. It shines with thermal emission from vast clouds of interstellar dust warmed by starlight. Even extragalactic sources, distant radio galaxies and quasars, add their own faint points of light to the interference. To remove this cacophony, satellites like Planck observe the sky at multiple frequencies, creating a kind of cosmic color filter. Each type of foreground emission has a distinct spectral signature, a specific color curve, while the cosmic microwave background has its own unique blackbody spectrum. Sophisticated algorithms analyze these multi-frequency maps, identifying and subtracting the contaminants to reveal the underlying cosmic signal. But this entire process rests on a critical assumption that our models for these foregrounds are perfectly accurate. What if they are slightly wrong? If the true behavior of galactic dust is more complex than our equations account for, or if there is an unknown population of faint radio sources, the subtraction will be imperfect. The algorithms might leave behind faint, structured residuals, ghostly patterns etched into the data that look for all the world like primordial anomalies. A large-scale asymmetry in the galaxy's dust distribution could mimic a hemispherical power asymmetry. An unaccounted-for ripple in the synchrotron background might be misinterpreted as a strange correlation. This is the constant, gnawing uncertainty for every cosmologist claiming a discovery. Is that alignment with the ecliptic a message from the Big Bang? Or is it just the final, uncancelled whisper of dust in our own solar system? The only way forward is to listen with ever sharper ears, to build instruments with greater sensitivity across more frequencies, turning down the volume of the local universe until the ancient signal speaks for itself. Even the most advanced satellite is a machine built by human hands, and every machine has its own subtle imperfections. The challenge of instrumental systematics is a constant reminder that we are not looking directly at the cosmos, but at a digital interpretation of it, filtered through lenses, detectors, and complex software. The Planck satellite, our most detailed mapmaker of the cosmic microwave background, had to be meticulously characterized down to the smallest detail. Its beam, the patch of sky it sees at any one moment, was not a perfect circle but had a slight asymmetry. The calibration of its detectors, ensuring that a specific reading truly corresponds to a specific temperature, was a monumental task filled with uncertainty. Even the satellite's scanning strategy, the specific path it traced across the sky over its multi-year mission, could imprint a very low level of repeating pattern onto the data. Teams of scientists spent years after the data was collected modeling and subtracting these instrumental fingerprints. For many of the large-scale anomalies, this is the most conservative and likely explanation. A tiny, unaccounted-for asymmetry in the instrument itself could easily mimic a hemispherical power difference or create a false alignment. This is why independent confirmation is the bedrock of cosmology. The fact that some anomalies, like the cold spot and the quiet quadrupole, were also seen by the earlier WMAP satellite, which had a completely different design and orbit, gives them tremendous weight. It suggests these features are truly painted on the sky, not etched into the lens of our telescope, yet the ghost of unknown systematics can never be fully banished. It is the ultimate caveat, the quiet voice that asks if we are finally hearing the universe or merely listening to the hum of our own magnificent machine. This inherent uncertainty is the final, frustrating wall we hit when staring into the cosmic depths. We are trying to understand the rules of a game by watching a single, solitary play. This fundamental limitation is known as cosmic variance, and it is the ghost in the machine of cosmology. The problem is one of sample size. When we study small-scale features in the cosmic microwave background, like the tiny hot and cold spots that seeded individual galaxies, we see thousands of examples across the sky. We can calculate reliable averages, confident that we have a good statistical picture. But when we look at the very largest scales, the grandest waves in the fabric of spacetime, our view shrinks to a sample size of one. Our entire observable universe is just one single realization of the largest possible patterns. Imagine you could only ever roll a pair of dice once to determine the rules of probability. If you rolled a 2, you might conclude that 2 is the most common outcome. But of course, that is just a fluke. Cosmic variance tells us that our entire sky, for all its vastness, might be that single, improbable roll of the cosmic dice. The strangely quiet quadrupole moment, the unexpected alignments, even the hemispherical asymmetry, could all simply be statistical quirks of our particular cosmic neighborhood. We might be living in a slightly unusual universe, one that is perfectly consistent with the standard model of physics, but just happens to look a little odd from our specific vantage point. This is why these large-scale anomalies are so difficult to interpret. They are whispers of a profound truth that could either be a revolution in physics or nothing more than a trick of perspective, a reminder that for all our knowledge, we are still prisoners within a single, magnificent experiment. A universe born from perfect symmetry should not contain defects, but what if the cracks were part of the design? Among the most dramatic possibilities are cosmic strings, not loops of string theory, but unimaginably thin scars in the fabric of spacetime. Think of them as one-dimensional cracks, formed when the fundamental forces of the universe froze into their current state, much like cracks form in ice as water cools. These strings would be under immense tension, possessing more mass than a galaxy packed into a width thinner than a proton. As they whip through the cosmos at near light speed, their immense gravity would create sharp, telltale edges in the cosmic microwave background. Light traveling from behind a cosmic string would be deflected by its gravitational field, creating a step-like discontinuity in the temperature map, a clean line where one side is minutely warmer than the other. It would be a flaw you could trace with your finger across the sky. Before the theory of inflation took hold, cosmic strings were a leading candidate for planting the seeds of galaxies. Their chaotic network could have provided the gravitational nudges needed for matter to clump together. Inflation, with its smooth quantum ripples, largely replaced this more turbulent picture. Yet cosmic strings have not vanished from the scene. The most sophisticated inflationary models do not completely forbid them. They could have formed at the very end of inflation, a secondary effect of the field that drove the expansion settling into its stable state. The hunt for these ghostly scars is a search for a specific kind of imperfection. Scientists have scanned the cosmic microwave background for the signature step-like patterns, but so far they have found nothing definitive. They have only been able to say how thin or how numerous these strings cannot be, placing strict upper limits on their existence. But the absence of proof is not proof of absence. A network of very faint cosmic strings below our current detection threshold could still be woven through the cosmos. Their subtle gravitational effects might be responsible for smoothing over some statistical anomalies or for creating peculiar alignments that our standard models struggle to explain. They represent a path not taken for the universe's main story, but a compelling subplot that could still be quietly unfolding in the background. The quiet uniformity of the cosmic microwave background could be hiding the ghosts of the universe's most violent infants. These are not the black holes born from dying stars, but primordial black holes, hypothetical monsters that may have formed in the first chaotic fraction of a second after the Big Bang. In that unimaginably dense and hot environment, random fluctuations in density could have collapsed under their own gravity, birthing black holes of almost any size, from microscopic specks to masses rivaling entire stars. If they exist in significant numbers, these primordial black holes are a compelling candidate for the invisible substance we call dark matter, but their influence would not have been silent. As they moved through the dense, hot plasma of the early universe, even before the CMB was released, they would have left a trail of disturbance. Their immense gravity would have pulled matter toward them, causing gas to accrete and heat up, injecting bursts of energy into the primordial soup. This energy injection could have subtly altered the thermal history of the cosmos, leaving faint spectral distortions on the ancient light, the kind of deviations from a perfect blackbody curve that future observatories hope to detect. Furthermore, as the universe expanded and cooled, the radiation emitted from matter falling into these black holes could have played a role in the epoch of reionization, the period when the first starlight tore apart the neutral hydrogen fog. This would change the optical depth, that crucial number we measure from the CMB's polarization, creating another potential mismatch between prediction and observation. The true power of this idea lies in its ability to connect two profound mysteries. It links the enigma of dark matter, which governs the largest structures in the cosmos, to the potential flaws in our oldest cosmic photograph. A specific pattern of anomalies in the CMB could, in theory, be the fossilized imprint of a hidden population of these ancient objects, yet the hypothesis walks a tightrope. Observations of star clusters, the subtle bending of light by gravity, and the recent echoes of gravitational waves have placed strict limits on how much dark matter can be made of black holes within certain mass ranges. The universe seems to allow only a narrow window for them to exist in significant numbers, but that window is not closed. The search for their imprint continues, a quest to find the subtle scars left by the universe's first and most secret inhabitants. Perhaps the problem is not with the story of the cosmos, but with the very rules we use to read it. For over a century, Einstein's theory of general relativity has been the unshakable foundation of our understanding of gravity, describing it not as a force but as the curvature of spacetime itself. It has predicted the bending of starlight, the existence of black holes, and the precise orbit of Mercury with breathtaking accuracy. On the scales of our solar system and even our galaxy, it is a flawless masterpiece. But the cosmic microwave background forces us to ask a radical question. What if this theory, for all its perfection in our local neighborhood, begins to fray at the edges of the observable universe? The anomalies we see could be the first signs that gravity itself behaves differently over cosmic distances and across cosmic time. This has led physicists to develop alternative theories of gravity, ambitious frameworks with names like F of R gravity and massive gravity. These are not replacements for Einstein's ideas, but extensions of them. Think of it like upgrading a map. A city map is perfect for navigating streets, but if you try to use it to sail across an ocean, it fails. You need a globe, a different kind of map that works on a grander scale. Similarly, these modified gravity theories propose that on the largest scales, the fabric of spacetime might have properties Einstein never anticipated. In F of R gravity, for instance, the strength of gravity could change depending on the curvature of space, becoming subtly weaker or stronger in the vast, empty voids between galaxy clusters. This would fundamentally alter how cosmic structures grow. The gentle gravitational tug that pulls matter together to form galaxies and clusters would operate under a slightly different set of rules from the very beginning. This would leave a distinct fingerprint on the cosmic microwave background, potentially explaining why the large-scale patterns appear quieter than expected, or why the lensing of the ancient light seems slightly too strong. The primordial sound waves would have frozen into a different pattern. Another idea, massive gravity, suggests that the gravitational force carried by hypothetical particles called gravitons has a tiny amount of mass. In our standard theory, gravity is massless and travels at the speed of light, allowing it to act instantaneously across the universe. But if gravitons have mass, they would travel more slowly, and their influence would weaken over immense distances. This could create a cosmic horizon for gravity itself, preventing the smooth synchronization of the universe on its very largest scales, and potentially accounting for the strange lack of correlation we observe. While these ideas are compelling, they walk a very fine line. Any successful modification must reproduce all the spectacular successes of general relativity in our local universe, while only diverging in the deep cosmic past or on the grandest of scales. It is a theoretical tightrope. So far, the pristine data from the cosmic microwave background has not demanded such a radical shift. The standard model, with its dark matter and dark energy, still provides the best overall fit. But the persistent anomalies are the cracks where the light gets in, the places where our magnificent theory of gravity might one day be forced to evolve. Perhaps the universe's initial conditions were not as simple as a single, smooth quantum hum. Most cosmological models rest on a foundational assumption that the first ripples in spacetime were purely adiabatic. In this elegant picture, every component of the cosmic fluid, from photons to dark matter, fluctuated in perfect sync. Where the density was slightly higher, everything was denser together. The ratios between different types of particles remained constant across the entire cosmos, a harmonious beginning. But what if the infant universe was not so perfectly coordinated? A more complex possibility exists, known as isocurvature or entropy perturbations. Imagine two different fluids, oil and water, swirling in the same container. In an adiabatic fluctuation, a wave would lift both fluids together, keeping their relative amounts the same, but an entropy perturbation is different. It is as if the oil became slightly more concentrated in one region, while the water stayed the same, creating a local imbalance in their ratio without necessarily changing the overall density. In the cosmic context, this would mean that in some patches of the early universe, the balance between radiation and matter, or between dark matter and ordinary atoms, was subtly skewed. One region might have had a tiny excess of dark matter relative to photons, while another had a slight deficit. The total energy density might have looked smooth, but the internal recipe for the universe was not quite the same everywhere. These entropy perturbations would have evolved differently as the cosmos expanded, creating a distinct signature in the way large-scale structures eventually formed. Their presence, even at a very low level, could be the key to unlocking several of the most stubborn anomalies. The strange lack of correlation on the largest scales, the hemispherical power asymmetry, even the puzzling quiet of the quadrupole moment, could all be echoes of a more chaotic and textured beginning. If the initial fluctuations were not purely adiabatic, but had a small component of this entropy variation, it would fundamentally change the predicted pattern of the cosmic microwave background. Detecting this signature would be more than just adding a footnote to the story of inflation. It would be a direct clue about the number and nature of the fundamental fields that drove the universe's exponential growth. The simplest models of inflation involve just one field, but if entropy perturbations are real, they point to a more complex symphony, with multiple fields interacting and decaying in the first instant, each leaving its own unique fingerprint on the fabric of spacetime. The hunt for this ghostly imbalance is a search for the true complexity of creation, a sign that the universe's first breath was not a single note but a chord. This quiet quadrupole, this strange hush on the grandest scale, forces a question that borders on philosophy. If our universe seems improbably calm, perhaps the explanation lies not within its own laws, but in the existence of a reality far vaster than we can observe. This is the radical proposition of the multiverse. Imagine not just one cosmos, but an infinite and eternal froth of universes, each with its own random set of physical constants and its own unique pattern imprinted on its cosmic microwave background. In such a boundless landscape, every possible configuration would exist somewhere. There would be universes with wildly powerful quadrupoles, others with none at all, and everything in between. Our universe, with its peculiarly subdued large-scale fluctuations, would simply be one among an infinite number. The reason we find ourselves here, the argument goes, might be a starkly simple one. This specific cosmic blueprint, for all its apparent oddity, may be one of the rare recipes that allows for the existence of galaxies, stars, planets, and ultimately, life. This is the anthropic selection effect. It is not that the universe was designed for us, but rather that we can only exist in a universe capable of producing us. A cosmos with a violently energetic quadrupole might have torn apart the delicate gravitational seeds needed for galaxy formation, leaving a sterile, empty expanse. Our universe's quiet beginning, then, would not be a flaw but a necessity, a statistical inevitability in an ensemble where observers can only arise in places suited for observation. This idea is as controversial as it is mind-bending. Its greatest weakness is also its most defining feature. it is, in its purest form, untestable. We are, by definition, trapped within our one observable bubble, forever unable to peek into the neighboring realities that the theory demands. Yet, for some cosmologists, it represents a logical endpoint, a way to make sense of cosmic coincidences that our current physics cannot explain. It transforms anomalies from puzzles to be solved into features of our particular cosmic address, a signature of our local neighborhood within a reality of unimaginable diversity. The multiverse hypothesis may never be proven, but its very existence as a plausible, if speculative, answer reveals just how deeply these 48 patterns challenge our understanding of everything. These ghostly whispers from the dawn of time demand a final verdict, and the tools to deliver it are now being forged. A new era of cosmic cartography is dawning, with observatories like the Simons Observatory and the colossal CMB Stage 4 project preparing to map the ancient sky with a precision that was once pure fantasy. These are not just incremental upgrades, they are quantum leaps in our ability to see. With thousands of new detectors working in unison from the pristine, dry air of the Chilean Andes and the South Pole, these instruments will achieve a sensitivity orders of magnitude beyond anything we have today. They will listen to the cosmic microwave background with such exquisite clarity that the current whispers of anomalies will either become a definitive chorus or fade into the statistical noise forever. The strange alignments, the hemispherical asymmetries, the puzzling quiet of the largest scales, all will be subjected to an ultimate test. The maps they produce will be so rich in detail that they will essentially allow us to run the universe's film backward with unprecedented accuracy, testing every assumption in our standard model. But their mission goes far beyond simply confirming or denying the patterns we already suspect. These new eyes will open entirely new frontiers of discovery. They will hunt for the spectral distortions, those tiny deviations from the perfect blackbody curve that could reveal cataclysmic energy releases in the universe's dark ages. And they will conduct the most sensitive search yet for the holy grail of cosmology, the primordial B-mode polarization, the curling signature of gravitational waves from inflation itself. Finding that signal would be like hearing the first tremor of the Big Bang, a direct observation of quantum gravity in action. The story of these 48 patterns is not a closed book. It is a prologue, a set of clues that have guided us to the brink of a deeper understanding. The next generation of explorers will not be looking at a faded, static-filled photograph, but a high-definition movie of the infant cosmos, where every flicker and shadow tells a part of the greatest story ever told. The true test of any cosmic whisper is not in isolation, but in its echo across the universe. This is the power of cross-correlation, a method that searches for hidden conversations between the ancient light of the cosmic microwave background and the universe as it exists today. By overlaying the map of the infant cosmos with charts of the mature cosmic web, scientists can listen for harmonies and dissonances that reveal the deepest workings of reality. The integrated Sachs-Wolfe effect provides the perfect example of what to listen for. As we know, this effect should create subtle warm and cold spots in the CMB where its light has passed through the evolving gravitational wells of superclusters and voids. This means there should be a specific, predictable correlation. If you look at a spot on the CMB map that is slightly warmer due to this effect, and then you look at the same direction in a map of galaxy distribution, you should find an underdensity, a vast cosmic void that is becoming shallower over time. Conversely, a cold spot in the CMB should align with a region where galaxies are densely clustered, a supercluster whose gravitational grip is weakening. This expected handshake between the oldest light and the present-day structure is a direct test of our model. but what happens when the handshake feels wrong? When the strength of this correlation does not match our predictions, it forces a profound question. Is the anomaly in the ancient light, or is it in the way the universe grew up? Perhaps the large-scale structure we see today is not what our models predict. Maybe there are more voids or more clusters than there should be, which would amplify or weaken the correlation signal. This multi-messenger approach turns a single mystery into an interconnected web of clues. An anomaly in the CMB that finds a corresponding anomaly in the distribution of galaxies is no longer a statistical ghost. It is a coherent signal pointing to a fundamental flaw in our cosmic story. It is the difference between hearing a strange noise in one room of a house and then discovering that the same noise echoes through every wall. This cross-correlation is the essential tool for building a picture that is not just based on a single snapshot, but on the entire life story of the cosmos, from its first breath to its present form. The persistent whispers from the cosmic microwave background have sent a clear message to the architects of our cosmic origin story. The simplest, most elegant models of inflation, the ones that produce a perfectly smooth and random universe, are now under immense pressure. The quiet quadrupole, the strange alignments, and the hemispherical asymmetry are like cracks appearing in a beautiful, but perhaps too simple, blueprint. In response, theoretical physicists are not abandoning the idea of inflation. Instead, they are building intricate new versions, models of stunning complexity designed to explain why the universe's infancy might have been subtly textured rather than perfectly uniform. These are not minor tweaks, they involve sculpting detailed features into the inflationary potential, the hypothetical energy landscape that drove the universe's hyper-expansion. Imagine this potential not as a single, gentle slope, but as a terrain with bumps, dips, and even plateaus. As the inflationary field rolled across this landscape, hitting these features could have caused brief pauses or surges in the expansion, imprinting specific, large-scale anomalies onto the cosmos. Other models introduce multiple interacting fields, a cosmic dance where different forms of energy vie for dominance in the first instant. This multi-field dynamics can create isocurvature perturbations, those initial imbalances in the cosmic recipe that could later manifest as the power asymmetries we observe. There are even proposals that challenge the simplest assumption about the universe's quantum starting point, known as the Bunch-Davies vacuum. Perhaps the universe began in a different quantum state, one that naturally produces the strange correlations and alignments that so puzzle us. The 48 anomalies, therefore, are far more than just problems. They are a compass. Each one acts as a constraint, ruthlessly eliminating whole families of theories while giving life to others. They force a creative revolution, guiding physicists toward a theory of the early universe that is infinitely richer, more complex, and ultimately, more true to the strange and wonderful cosmos we actually see. These subtle patterns are more than just data points, they are doorways to a much deeper question. What if the universe is not just complex, but fundamentally strange in ways that challenge our most cherished philosophical principles? The Copernican principle, the idea that we do not occupy a privileged or central position in the cosmos, is the bedrock of modern science. It is the reason we assume the laws of physics are the same in a distant galaxy as they are here on Earth. But the persistent alignments, the hemispherical asymmetries, and the other anomalies whisper a troubling possibility. What if our cosmic address is, in fact, special? The eerie alignment of the quadrupole and octupole, moments with the plane of our own solar system, feels like a cosmic coincidence of impossible proportions. If it is real and not an artifact of our measurements, it suggests that the largest scales of the observable universe are somehow linked to our infinitesimally small local neighborhood. This would not just be a scientific curiosity, it would be a philosophical earthquake, forcing us to reconsider humanity's place in the grand scheme of things. Are we merely passive observers of a universe that operates on impartial laws, or is our vantage point somehow woven into the fabric of reality itself? The implications ripple outward, touching even our understanding of physical law. We operate on the assumption that the constants of nature are uniform across space and time. But if the universe exhibits a genuine, large-scale asymmetry, could it be that the strength of gravity or the mass of an electron varies subtly from one cosmic hemisphere to another? This idea that the rulebook of reality might not be consistent is perhaps the most profound challenge these anomalies present. They force us to confront the humbling limits of our knowledge. Our entire scientific worldview is built on a foundation of assumptions, from the isotropy of the cosmos to the uniformity of nature. The cosmic microwave background, the one fossil we have from the dawn of time, is now suggesting that foundation might have cracks. Studying these 48 patterns is not just an exercise in data analysis, it is a form of cosmic introspection. It asks us to consider whether the universe we see is the only possible universe, or merely the one we are conditioned to perceive. The search for answers is ultimately a search for our own relationship with the cosmos, a journey that began with a photograph and may end by redefining reality itself. The overwhelming complexity of the cosmic microwave background forces us to evolve our search. With 48 potential anomalies whispering from the data, traditional statistics are reaching their limits. The next great leap in understanding will not come from a human eye scanning a map, but from an artificial mind learning its deepest language. This is where machine learning enters the story, transforming anomaly hunting from a careful inspection into a deep exploration. These algorithms, particularly powerful tools known as convolutional neural networks, are designed to excel at exactly this kind of task. They work not by being told what to look for, but by learning the fundamental grammar of the cosmic microwave background itself. Think of it as teaching a computer the difference between a serene, classical symphony and the chaotic noise of a busy city street. The algorithm is fed thousands of simulated maps of the CMB based on our standard cosmological model. It learns every nuance of what a normal, statistically random universe should look like. Once its training is complete, it is unleashed on the real data, the actual map of our sky. Its purpose is to find the cosmic equivalent of a wrong note, a rhythm that breaks from the established pattern. The power of this approach is its ability to perceive subtlety. A neural network might detect a specific, non-local correlation between distant cold spots that a human researcher would never think to test for. It could identify a faint, swirling texture in the temperature variations that is too complex to describe with simple equations. These machines are not biased by our preconceptions of what an anomaly should be. They are free to discover entirely new classes of strangeness, patterns that defy our current vocabulary. Furthermore, they offer a path to resolving the agonizing debate over statistical significance. By generating millions of mock universes, machine learning can provide a much more robust probability that a given feature is a real signal rather than a random fluke. It can quantify the look elsewhere effect with a precision that was previously impossible. The future of cosmology will be a partnership where human curiosity poses the great questions and artificial intelligence helps us decipher the answers hidden in the light. These whispers from the dawn of time lead us to the most fundamental level of reality. The cosmic microwave background is not just an ancient photograph, it is a quantum mechanical artifact. Those infinitesimal ripples in temperature, the seeds of all galaxies, are believed to have originated as quantum zero-point fluctuations. In the empty space of the quantum vacuum, particles and energy flicker in and out of existence, a seething foam of potentiality. According to our leading theories, the violent expansion of inflation seized these quantum jitters and stretched them across the cosmos, freezing them into the gravitational hills and valleys that would shape everything to come. This means the map we study is a direct imprint of the quantum world, magnified to a scale of unimaginable proportions. Therefore, the anomalies we find are not just cosmic curiosities. They could be profound clues about the nature of quantum theory itself. Perhaps the strange alignments and asymmetries are signatures of physics operating beyond our standard quantum mechanics. The most tantalizing possibility involves quantum gravity, the holy grail of modern physics. We have no complete theory that unifies the quantum world with Einstein's theory of gravity. The first instant of the universe when inflation occurred was the one moment when quantum gravity effects would have been dominant. Is the hemispherical power asymmetry a fossilized record of how spacetime itself emerged from a quantum state? Could the quiet quadrupole be a sign that the quantum vacuum was not perfectly uniform, but possessed a subtle structure we have not yet imagined? This line of thinking connects the very large to the very small in a way that no laboratory experiment ever could. The cosmos becomes a particle accelerator of ultimate power, and its first light is the data readout. To decode these patterns is to read the first chapter of a story written in the language of quantum gravity, a chapter we are only just beginning to understand. These faint imprints are a message that has been in transit for over 13 billion years. They are the oldest communication in existence, a signal sent from the universe's infancy that we are only now learning to decipher. Each subtle variation in temperature is a word in a cosmic language, a direct transmission from a time before time as we know it. Unraveling this code is far more than a technical achievement in data analysis. It is the ultimate act of cosmic archaeology. Unlike digging through layers of sediment to find shards of pottery, we are sifting through the emptiness of space to recover the original blueprint of reality itself. We are not inferring the birth of the cosmos from its later remains. We are reading the first chapter of its history directly from the sky, a chapter written in the language of primordial heat and gravity. This light is a time capsule of unparalleled fidelity, carrying an unaltered snapshot of the universe at the tender age of 380,000 years old. Every anomaly, every strange alignment, is not a flaw in the data but a potentially crucial sentence in that opening chapter, a sentence we have not yet fully translated. The act of mapping the cosmic microwave background is like holding the universe's baby picture, and in its faint smile and curious gaze, we are searching for the secrets of its entire life. This is the true power of a mystery, a force that compels us to look deeper. Throughout the history of science, the greatest leaps forward have not come from confirming what we already knew, but from confronting the data points that stubbornly refused to fit. The slight wobble in the orbit of Mercury was a tiny anomaly in Newton's clockwork universe, a discrepancy that could not be explained by known planets or gravitational pulls. It was this very puzzle that helped pave the way for Einstein's theory of general relativity, a complete reimagining of space, time, and gravity. The unexplained became the essential clue. The 48 hidden patterns in the cosmic microwave background stand as a similar challenge today. They are the modern equivalent of Mercury's precession, a collection of cosmic wobbles that our current standard model cannot fully account for. The ultimate resolution may not be as dramatic as overturning our entire understanding of gravity. It is entirely possible that many of these anomalies will be explained by subtle instrumental effects we have not yet modeled, or by the simple, sobering fact of cosmic variance. the statistical fluke of living in a universe that is just one single realization of many possibilities. But even in that scenario, the pursuit is far from a failure. The rigorous investigation of these whispers forces a revolution in our methods. To test if the cold spot is a window to another universe, we must first build telescopes of unprecedented sensitivity. To determine if an alignment is real or a ghost in the machine, we must refine our data analysis to an art form, creating new statistical tools and machine learning algorithms capable of seeing patterns invisible to the human eye. The process of chasing down these ghosts, of trying to prove ourselves wrong, is what sharpens our tools and clarifies our thinking. Each proposed explanation, whether it involves exotic new physics or a more nuanced understanding of our own instruments, pushes the entire field of cosmology forward. The anomalies act as a compass, pointing not necessarily to the final answer, but to the specific weaknesses in our current knowledge. They show us where our models are brittle, where our assumptions are untested. In doing so, they guarantee that our next model, whatever it may be, will be stronger, more robust, and more deeply connected to the true, strange nature of the cosmos we are so privileged to observe. The search for these cosmic truths resonates far beyond the pages of scientific journals. It captures a deep and universal curiosity, a yearning to grasp the grand story of which we are a small part. When we learn that the universe's blueprint contains 48 flaws, it does more than challenge a theory. It touches a primal human need to find meaning in the vastness. The idea that our most fundamental picture of reality might be incomplete is not a frightening prospect, but an exhilarating one. It returns a sense of wonder to the cosmos, a feeling that the universe is still a place of profound mystery. This is not the mystery of a puzzle to be solved and forgotten, but an ongoing dialogue between humanity and the heavens. Every unexplained alignment, every strange cold spot, is an invitation to look deeper and ask bigger questions. They remind us that the greatest discoveries often begin not with answers, but with a single, beautiful anomaly that refuses to go away. Yet the ultimate meaning of these 48 whispers may lie not in their individual strangeness, but in their collective voice. Each anomaly, from the axis of evil to the faint spectral distortions, is a unique puzzle, but together they form a chorus, a unified call for a deeper understanding of reality. They are not random errors scattered across the data. Instead, they cluster in specific ways, pointing toward the same potential weaknesses in our foundational story. The quietness on large scales, the unexpected alignments, and the puzzling tensions all suggest that our standard model, for all its power, is a magnificent approximation, not the final word. This is not a failure of cosmology. It is its greatest and most thrilling success. A perfect model that explained everything would be a dead end, a closed book. The Lambda CDM model has brought us to the very edge of understanding, and now these anomalies are the signposts showing us precisely where to step beyond. They are beacons in the dark, illuminating the path toward a more complete theory. That next theory could take many forms. Perhaps it is a subtle modification to the story of inflation, adding a layer of complexity to the universe's first moment. Maybe it reveals a new, unexpected property of dark matter, allowing it to interact in ways we never dreamed. It could demand a revision of Einstein's theory of gravity on the largest cosmic scales, or it might point toward something entirely unforeseen, a new force or a new particle that operated only in the extreme environment of the Big Bang. The specific destination is unknown, but the direction is clear. These patterns are the universe's way of communicating the limits of our current knowledge, and in doing so, they invite us to write the next chapter in the story of everything. The sheer number of these whispers is itself a message. Stepping back from any single anomaly, the collective portrait is one of a model under strain. Our standard model of cosmology, lambda-CDM, stands as a monumental achievement. It has predicted the distribution of galaxies, the detailed peaks of the cosmic microwave background, and the accelerating expansion of the universe with breathtaking accuracy. It is a framework of immense power and elegance, yet its brilliance casts sharp shadows, and it is in those shadows that the anomalies gather. The Hubble tension and the S8 tension are the loudest and most statistically significant of these discordant notes, but they are joined by a chorus of quieter irregularities. The quiet quadrupole, the strange alignments, the hemispherical asymmetry, all seem to point toward the same conclusion. On the very largest scales, the universe is subtly but persistently different from what our best model predicts. This is not yet a crisis that shatters the foundation. Instead, it is a compelling and consistent invitation. The model is not broken, but it is incomplete. The cracks we see are not signs of collapse, but openings, windows into a deeper layer of physics that we have not yet grasped. They are clues left by the universe, hints that the story of dark energy, dark matter, and inflation is richer and more complex than we ever imagined. The question is no longer if there is something to discover, but what form that discovery will take. And the answer lies in the tools we are now building to listen more closely than ever before. The faint glow of the cosmic microwave background, once thought to be a simple and smooth echo of the Big Bang, has revealed itself to be a complex and deeply mysterious text. The 48 hidden patterns we have explored are far more than mere errors in the data. They are profound questions written in the fundamental language of the cosmos. Each anomaly, from the axis of evil to the Hubble tension, directly challenges our core assumptions about a uniform universe, a simple inflationary birth, and the immutable nature of physical law itself. Some of these whispers will undoubtedly fade away as our observations grow sharper, revealed as statistical phantoms or subtle instrumental quirks. Yet others may very well blossom into the next great scientific revolution, forcing a rewrite of the story of everything. The journey to truly understand these patterns is only just beginning. It will demand telescopes of unimaginable sensitivity, algorithms of brilliant cleverness, and theories of breathtaking boldness. So the next time you find yourself looking up at the night sky, remember that you are not just seeing stars. You are witnessing the magnificent aftermath of a grand event, whose deepest and most startling secrets are still encoded in the faint, ancient light that permeates every corner of the void. What other cosmic mysteries are waiting to be found, hidden within the silence between the stars?